Good morning, students. Myself, Dr. Eustace Russell, working as Assistant Professor in the Department of Mechatronics Engineering at Sri Muthukumaran Institute of Technology. So now so far we have seen the subject called Robot Dynamics and Control. For the part 1 and part 2 we completed. Previous class we have seen various static forces acting in the manipulators, we have seen Jacobian matrix we have seen, and followed by some basic concept also we covered in the last session. In this video, again we are going to discuss the unit 1 only, robot force models. In that the remaining topics we will see in the upcoming slides one by one. So this is the syllabus. In this today we are going to concentrate in Cartesian transformation of velocities and static forces, and followed by some basic problems also, as well as in the matrix form we will do some derivation part also. So Cartesian transformation of static force. Why is this important? That is the first thing we have to notice this point. Why this is important? That is, CFC and CNC can be the force sensor readings, but our primary interest is BFB and BNB, that is force and moment at the tool tip. As a force sensor readings can be utilized, will be there, and by that the final interest is that at the tool tip what are the force that is acting at the tool tip we have to be noticed. So in this left hand side there is a force sensor is there. But finally the tool that is operated, the tip tool, how the force and the movement that is transmitted to that. So for equilibrium condition, already you might have covered this concept in engineering mechanics. That is, under equilibrium condition, summation of forces is equal to 0 and summation of normal forces is equal to 0. Then AFC plus AFR equal to 0 and AFR equal to minus AFC, and ANC plus APB minus APC into AFR plus NR equal to 0. And along that, ANR equal to minus ANC minus APB minus APC into AFR. In the diagram, we are taking the forces that is acting over in the system. And also, AFB equal to minus AFR, and also AFB equal to AFC. Followed by this slide, we are going to simplify this. A and B equal to minus ANR equal to ANC plus APB minus APC into AFR. A and B equal to ANC plus APB minus APC into minus AFC. And upon simplification, you will get ANC plus APC minus APB into AFC, because you took the minus common. Minus into minus will become as positive. And again we can write as a product of these two things, and we can write in these terms. In matrix form also we can write this. That is AFB, A and B, both the left hand side we can write, and put in the right hand side as I and A or B, B, PC, X, 0, 1. That is the matrix form we are going to write. The multiplication of AFC divided by ANC. This represents the force torque Jacobian transformation. But in typical applications, we should like to relate CFC, CNC with BFB, BNB. Sensor readings will be expressed in local frame of sensor. We can transform vector F and N like any other vector via rotational matrices, that is AFC, ANC, ARC, the corresponding diagonal values also ARC, followed by CFC and CNC. So this is we already wrote as a Jacobian matrix, the distance coverage, that is a multiplication of that also we have noticed here. Then followed by again the expression goes on like this: A of B, A and B equal to I divided by A or B, B P C X, and A or C, diagonal ways A or C, C F C, C and C, A of B, A and B equal to A or C, A or B, B P C X, A or C, and A or C corresponding we have written this, and CFC and CNC, and here also the same thing: B of B and B and B, B or A and B or A of B, A and B. Again, the Cartesian transformation of static force is followed as B of B, B and B equal to B R A, B R A, followed by A R C divided by A R B, B P C X, A R C, A R C, and C F C, C N C, and it is represented again B R A, A R C, B R A, A R B, B P C X, A R C, 0. In the next diagonal ways, we are going to write B R A, A R C. That diagonal ways, it should be similar. Followed by the last thing is the tool. What is the output we are getting? That is CFC, CNC. Then after the various simplification, we will get the final step: BPC into BRC, CFC, that is equal to BPCX, BRC, CFC. Then Cartesian transformation of static force, that is B of B, B and B equal to BRC divided by BPCX, BRC, and 0, BRC, followed by CFC and CNC. So hereby we are going to discuss one derivation type of problem. The problem goes on like this: find the inertia tensor for the rectangular body of uniform density rho with respect to coordinate system as shown in the figure. That is 6.2. A sketch is given. What is dV mean? dV means dx, dy, dz, ixx, that is corresponding to 0 to h, 0 to L, 0 to omega, y square plus x square, rho, dx, dy, dz, and also followed by 0 to h, 0 to L, y square plus z square, omega. So what we have done means, here we are going to differentiate, that is x, dx, differentiation of dx, sorry, integration of ds, what you will get means x, and applying the limit, that is omega, then finally you will get omega rho dy dz. Again we are going to differentiate with respect to, sorry, we are going to integrate with respect to y, and followed by again you will get, what will happen means y square will become y cube by 3 plus z square L. Why this L means we are going to apply the limit. In place of y, we are going to apply the upper limit. That's why L cube by 3 plus z square L. Then again, the last differential form is dx, and integrate with respect to dx. Again, it will become so omega. Every time you will get one omega. So omega we are taking inside the bracket, as well as height will be accompanied in that height. And here also, in terms of z square will become z cube by 3. In the place of z we are going to apply h. Finally, what you are going to do means, the common term you are taking out. By that you will get the final relationship. The final relationship you will get like that, because where m is the mass, total mass of the body, permuting the terms you will get ixx and izz and iyy. Iyy is nothing but m by 3 omega square plus h square, and izz is nothing but m by 3 L square omega square. So this is one type of derivation type of problem. Finally you will getting the expression. And also parallel axis theorem you might have studied in engineering mechanics. The same thing here also. Ixy final expression you are getting m by 4 omega L. Then Ixz is equal to m by 4 h omega, and Iyz is equal to m by 4 hl. Inertia tensor for this object we are going to write in a matrix form. Here we can see in the left hand side, that is 6.24, the matrix form is written. The parallel axis theorem is nothing but inertia tensor changes under translation of the reference coordinate system. Parallel axis theorem relates the inertia tensor in the frame with origin at the center of the mass to the inertia tensor with respect to another reference frame, where C is located at the center of mass of body and A is the arbitrary translated frame, followed by AIXY is equal to CIXY minus MXCYC, and followed by PC equal to XC YC ZZ. Locates the center of mass relative to A. Remaining moments and products of inertia are computed from the permutation of the x, y, z in that equation. Finally, you are getting AI equal to Ci plus M PCT PC I3 minus PC PC T. I3 is the 3 by 3 identity matrix. So these are the references which I took for preparing this content. Kindly go through the references. Thank you, students. Thank you for your kind attention. For this unit 1, we completed part 3 topics. Some more derivative part, kindly write and study, then only it will be easy. Kindly subscribe the channel and share to your friends. Thank you.